The conference is almost at its end, unfortunately, but don't beware, because we still have an awesome talk left here on this stage. And I won't bore you, because I'm not the one who's going to talk. We're going to have an amazing talk instead. So, here we have Markus Boberg, who's going to talk about the problem with multiplayer. Welcome up.
Thank you very much. First off, I think I'm going to say, I'm actually going to point at my PowerPoint, and it's good to see it. And I noticed over there you can't really see it because the mic, etc., is away. So it would be good to get a good view of the PowerPoint. And I also have to say that I appreciate the discussions and the talks about imposter syndrome that's been going on here. Because you'll notice in like 2 slides, that's something I would be prone to. So yeah, let's get started. We're going to talk about the problem with multiplayer. And first off though, who am I? I'm Markus Boberg. I'm a senior network programmer at Mediatonic. I'm working on Fall Guys. I work mainly in the mid and low level networking, as well as the core of the multiplayer solution. Quick about my background, and this would be the second slide then. I'm actually a nurse. I've been working as a nurse for 4 years. Then I took a master's, became a nurse anesthetist, worked in surgery for 3 years, and then I chose to go for what I really wanted to do. I really wanted that too, but it's always been in my mind that I wanted to work with games and especially multiplayer. So I actually went down in time. I worked 40% and decided to do my own multiplayer project to learn multiplayer. I haven't gone to school for it. I just dig in by myself. And after those 1.5 years, while working 40%, I had to kind of quit my job at the hospital because they wanted me at 100% or nothing. So then I was without a job, and eventually I got headhunted 3 times in a row and ended up at Mediatonic and Epic Games. And that's how I'm here, and hence the tendency for imposter syndrome. If you are interested in multiplayer networking, I would just say now is the time to become a network engineer or a multiplayer designer or a multiplayer programmer, whatever you want to focus on or call yourself. You don't need a bachelor degree. Of course, it helps, yeah, but you don't need it. There's a lot of studios that are looking for people with multiplayer knowledge and that are focused on it, that really want to get into the field. And a few tips first for those who want to get into it. Don't take shortcuts. Like, go into the low-level stuff. Go use open source materials. Pick it apart. Each open source solution often have example projects. For example, an open source solution for a network library. They usually have an example project in the engine it's supposed to be used in. So for example, in Unity, take that example project, pick it apart, look at the different solutions it's using, and do this in many different example projects, because not one example project will have the truth. They will have parts that are good, parts that are bad. You need to go through it and learn from it all and build your own library, so to speak, with solutions and so in your head. And choose the hard route. After you've done a first pass, take a look at what don't I really understand about networking or multiplayer. Pinpoint the areas and dig into that, and or create small games that would challenge you to solve those problems. So you have to solve them to complete that small game. experiment a lot. I used to draw up the flow for the multiplayer, and that helps me a lot to visualize like start to end what happens in the multiplayer solution, and step out of your comfort zone. It's okay not to know stuff. Like it's okay to go in. How do you say it? In over your head, because you can solve it. You can figure it out. The first time doing something is the first time you're doing it. Don't be afraid. Don't put it off just because you haven't done it before. And yep, with that said, let's quickly just say that there are different network architectures you can use. For example, peer-to-peer. Every client connects to other clients, either everyone to everyone or everyone to the host, where the host is the source of truth in the game state. Mainly used by indies, smaller multiplayer games, etc. And then we have dedicated server, where every client connects to a dedicated server running somewhere. And that dedicated server is running the game. So every player is there, the game world is there, physics run there, everything runs there, just no local player. And then we have host via relay, which is essentially the same as peer-to-peer, but with a little more safety. You can connect to a server that's just relaying the data, so you don't have to connect directly to someone else's computer or open a port on that computer. You have this safety in the between, but you don't run the game on that relay server. But the main part that I would recommend people to learn is dedicated server. That's the most used, and if you can work with that, you can probably work with the others. So the problem of multiplayer is latency. And latency is a word for a delay. And we have a delay from A to B. Latency in itself doesn't say anything unless you define it. And here we have a few different definitions or parts that we like to talk about. For example, we have network latency. That's the time it takes for data to travel over the internet from its point of being sent to where it's arrived at. And then we have application-based latency. That's, for example, when you receive data, you receive that at any point, but your update loop needs to get to the point to actually process that. And that takes time. If you have a FPS for 100 FPS, then one update loop takes 10 milliseconds. So it can take up to 10 milliseconds before you actually process that incoming data. And that's significant when it adds up. And you need to know that it's there, that it's happening. And I don't use lag as a terminology or ping. I tend to use RTT, which is round trip time, because that's an A to B definition of latency. It's a round trip time. It's from the local down to the server and then back up from the server to the local. So it's a round trip. And that includes both network latency and application-based latency. You can see there's represented here by 5 milliseconds in sending and receiving, and then sending and receiving. It's not 5 actually. It can be 1, it can be 10, it can fluctuate, etc. But it's there. And then we have another latency to consider. That's local down to remote. And the remote is my local player view on your screens. Because my player is that it exists on my computer, it's existing on the server, and it's existing on your computers. So it's my local player, the server player, and the remote player of my player. And we have a latency between those. So we have the local to remote latency. We have my local is sending data down to the server, that takes time, and then the server sends that data down to the remote, and that takes time. And that's essentially half of my RTT between me and the server, and then half of your RTT towards the server. And that's the local to remote latency. And we can visualize this a little bit. Here we have Fall Guys. And I should say also, what I'm showing in the different things, that's not solutions or etc. in Fall Guys. I'm using Fall Guys as a way to visualize the problem of multiplayer. Hopefully next year I can do a talk of actual solutions in Fall Guys. But to the left here, we can see the server. There are two characters, they're running hand in hand. On the right side, we see a client, and that's the white player's local client. And if you look real close, the white player on the client side is actually in front of the server. It's real close, but it's in front of the server because the client does something and at the same time sends that to the server, and that takes time. So the local is in front of the server, and then the server sends that to the remotes. And that's essentially what's happening to the red player or pink player. On the client side, it's behind where it is on the server, and it's quite far behind the local player. So there's a discrepancy there between the local and the remote due to the local remote latency. And if you were to look at it from the client of the purple player, that would be reversed. So the white player would be behind and the purple player would be in front. So think about these running towards a finish line. Like the local player would see themselves win, the other one would see themselves win, and the server would draw the tie and people would rage. I have another way of visualizing this issue. In Fall Guys we have a game mode called tail tag, where some people start with a tail, others need to grab the tail, and then when the game is over, those who have a tail win and go on to the next round, and the others are eliminated. And here we can see 3 rows and 2 players. We have one blue player, player 1. We have one purple player, player 2. If you look at the top row, you can see that the purple player 2 is the local on that row, while the other one is a remote on that row. If you're looking at the bottom, you can see that the blue player 1 is the local, and the player 2 is a remote. And we have a distance between them, essentially what I showed you before. What's happening, the situation here is that the one with the tail, the yellow, I'm not an artist, so the one with the tail is running from the blue player, and the blue player is chasing. And if we look at it from the blue player's perspective first, from the local player 1 sends its data up to the server, takes 60 milliseconds. So the server sees that player 60 milliseconds in the past, or delayed. The server sends that to the local player 2's machine, and that takes 45 milliseconds. That makes a total of 105 milliseconds local to remote latency. So the local player 2 sees that player 105 milliseconds back in time. And we can follow the other way around. Local player 2 sends its data to the server, takes 45 milliseconds. Server sends to local player 1 at the bottom, and that takes 60 milliseconds. So there's a 105 milliseconds discrepancy there also from local to remote. And this ends up that the one with the tail sees the other one far behind. Like they can't grab my tail now because they're over there. While the one chasing, they see themselves just there. They can grab the tail, they think. And on the server, it's somewhere in between, due to the server being between these two local to remote latencies. And also, as you can see, it's 60 milliseconds to the tail grabber, the lower, and it's 45 to the player 2 local. That's because they have their own RTT towards the server. So it's the player 2, the top row, has a lower RTT round trip time towards the server than player 1 has. So it's how you see remotes are based on both their internet and your internet. If you have good internet and someone else has a bad internet, you will still see that player further up behind than they're actually like your view of them will be affected by their internet, essentially. Let's look a little bit about how remotes work then, because remotes aren't usually, at least, handled in the same way as the local player. When I'm playing locally, my inputs move the character in update or a fixed update loop, if we're using physics. That's not really what's happening for remotes. They're getting data from the server called snapshots or states or whatever you want to call them. I'm going to say snapshots because I'm used to that. And they're being sent from the server to remotes with some specific time steps. Here it's 50 milliseconds apart, but we need to render them out between those 50 milliseconds because we're running at 100 FPS, we're running 10 milliseconds update loops. What we use then is interpolation, and that's the creation of new data points between known data points. So here we have snapshot 1 and we have snapshot 2. If we want to render out the player at 25 milliseconds, we would end up over there because in this case we have two positions. We also have an incoming and an outgoing velocity. And we take those into consideration. So it's moving slightly upwards, but it's going to arrive at a point going slightly downwards. And that creates an interpolation which ends up in this arc. We can also do a simpler interpolation, just a straight line between them, not take velocity into account. It works, it's just not as accurate. But what if we don't have a target data point or target snapshot? For example, below here then. Then we use extrapolation. That's the creation of new data points based on previously known data points. So if you arrive at snapshot 2 and then we don't have a snapshot 3, then a simple way of doing it is just take the current velocity and use that to extrapolate where the next position will be at this time step. And when you're extrapolating, you're just predicting. You don't know what's going to happen. I switched the slides a little bit early here, but it's going to be quick. When you're extrapolating, you don't know what's actually going to happen after you past snapshot 2. You're just predicting what will happen. It could be turned up. And then when you receive a new snapshot, you need to correct that. You need to correct the wrong prediction that you had. And that's called reconciliation. There are mainly two different ways of approaching, or rather talking about reconciliations. You can do it in a lot of different ways, but there's hard reconciliations and there are soft reconciliations. For example, when I drag that remote over the edge on the other side of the wall, it wants to try to get back to its snapshot position, which is standing still there. But it knows that I can't get over there in a graceful way, so it just snaps back. That's a hard reconciliation. While I move it in the Z and X axis, like now and there, it just gracefully slides back to its original position where it should be. It's not as invasive as just snapping to where it should be. And there's a lot of prediction going on behind the scenes in a multiplayer game. due to latency, due to this discrepancy between local and remote. So reconciliation is a large part of multiplayer programming. So the best part of viewing or rendering out a remote player is through interpolation. And the one way of approaching that, to mainly use interpolation and not go into extrapolation, which is a dangerous thing since you're predicting it. You don't know actually, which you mainly do with interpolation. How to solve this is to use a snapshot buffer, for example. That's one of the solutions for it. Then when we receive a snapshot from the server, we buffer it. And then we receive a new one, and we buffer that. And when we have a couple of those, we can start rendering out between those we already have. So in this case, we're rendering out the player 75 milliseconds back in time because we've buffered up 3 snapshots. And we have our current simulation time, and we use snapshots from 75 milliseconds back in time. And that makes it so that when we arrive at snapshot 2, we already have snapshot 3 to start interpolating towards. And if we don't have snapshot 3, we can extrapolate for a little while, and then we will receive a new snapshot, and then start to interpolate and reconciliate at the same time. And this is it's the main documented approach for remote replication. But there's a lot of you can be really creative working with remote replication, and that's something we've done in Fall Guys, for example. Because if you think about it, this adds latency between local and remote. We're not using the snapshots that arrive, we're buffering them and use them 75 milliseconds later. So in this problem we saw, whether local and remote see the scenario in 2 different ways, that gets worse. So the local player 1 sends data to server sends it up to local player 2, and that just buffers it and renders out the player 75 milliseconds even further back in time. So the player is now even further away from the one with the tail. And that one with the tail feels even safer, like he will never grab my tail. While the opposite, the other way around, the one with the tail sends its data to the server sends a snapshot down to the local player 1, which buffers again and renders that player out 75 milliseconds back in time, which put that player even closer. They're almost bumping into them. And they start raging even more that they can't grab the tail. And the server is still the same. The server has the same distance between them. I'm going to leave latency behind there. I just wanted to show the problem with multiplayer there. And I'm going to talk a little bit about network data. When we're sending network data, we're passing over a byte array to the socket. So a byte is the lowest variable you can send, or rather the only variable you can send. So if you have an int, or a float, or an enum, or a bool, it serializes and becomes a byte. So an int becomes 4 bytes in an array. And then you take those 4 bytes on the receiving end, deserialize them into an int again. And if we look at server-side outgoing data, we can calculate that by taking the bytes that needs to be sent times the entities that want to send those bytes times the clients that should receive those bytes times the send rate that we're sending the bytes in per second. And that equals amount of bytes per second that's going out from the server. And if we look at that unoptimized, the left list, we have an example where we have 52 bytes. That's position, velocity, rotation, and angular velocity. That equals 52 bytes. We have 80 entities, that's 60 players and 20 objects, for example, that should be networked and synced. We have 60 players, or 60 clients rather, and a send rate of 30 times per second. That equals 7.5 million bytes per second, which is 52 megabits per second. And the server can handle that, yeah, but it should handle it all the time. It should be constant, and having thousands and thousands of servers sending data or sending 57 megabits per second is quite expensive. And if we look at an optimized view of this, we can optimize those variables, position, velocity, rotation, and angular velocity, down to 15 bytes. We still have 80 entities that need to send them. That can also be adjusted and experimented with, of course. But in this case, we still have 80 that send those bytes, 60 clients, but we lower the send rate also a bit. And the better your remote replication logic is, the lower the send rate essentially you can have. So if you have a good remote replication with good extrapolation, good reconciliation, the less times you need to send snapshots from the server to that remote. This new optimized equals 1.5 million bytes per second, which is 11 megabits per second, which is quite a lot better and saves it. The server gets more stable, and it saves a lot of money doing this. And it's also really interesting for a network programmer to get these variables down to just those bytes and still have precision in them. They still have accuracy in a position and rotation and velocity. So how can we, first off, what should we think when we choose a variable, or a type rather? If we have health that goes from 0 to 1000, we don't need to use an int. As you can see in the calculation to the right there, an int uint in this case can handle 4 billion, almost 300 million as a max value. We don't need that range for a value that's only going to go up to 1000. At the bottom we have a byte that can have a max value of 255. That doesn't fit either. So the best fit here would be a short or a U-short, which can hold 65,535 as a max value. So this is a simple thing that everyone should do in this field. Just which variable should I use to just fit the values I need? That saves 2 bytes. Usually people just use an int because it's the normal. But using a U-short here saves half of the traffic. But we can do more than this. A U-short is 16 bits. We don't need those 16 bits because they added up to 65,000 plus in a max value. So we can check how many bits we actually need to use to send those 1,000 or 1,000 as a max value. And then we have 2 raised by 10 minus 1 equals a max value of 1023, and that fits our 1000 that we need to send. So we need 10 bits to send that health. stamina, that health value. And now we need to send health, stamina, and mana. That's 3 of those. So 3 times 10 equals 30 bits that we want, but we can only send network data as sets of 8. A byte is 8 bits, and a byte is the lowest thing we can send. So we take 30 divided by 8 equals 3.75 bytes. You have to round it up since we only can send full bytes. And that makes us, and that puts us at 4 bytes. So we can send these 3 variables as 4 bytes. And to do that, I visualized health with 10 bits, stamina also 10 bits, mana 10 bits. And we can use bit shifting and bit OR operator in this case to put those together inside one int, because one int is 4 bytes. So what we do is we take health, shift it 20 bits to the left, and an OR operator, and then stamina, shift that 10 bits to the left, and then an OR operator, and then mana. And that adds up those bits into one integer. The integer will be a random number because it's going to read the bits that's in it. We don't care about the number in the int data there. We care about the bits in it. And then we can take that int and serialize it to a byte array. And that byte array would be seen as like that. First you have mana, and then 2 bits of mana in the next byte, and then stamina and 4 bits of stamina in the next byte, and then health. And then at the end you have 2 bits that are unused. But that's a lot better than having 6 bits per variable if we were to put health, stamina, and mana in U-shorts by themselves, because a U-short is 16 bits and we use only 10 of them. And if you want to min-max even more, you can use those 2 bits to put in booleans via the same technique. Because a boolean is either a 0 or a 1. That's true or false. And that's where I'm going to say thank you for being here, for showing interest. And I'm also going to leave you with a few useful sources that you can take a photo of. It's some of the things that I used just when I did my first research. I went through it all, I read it, and then I pinpoint what don't I really understand with it. What in the whole, like the whole solution of doing a multiplayer game doesn't add up to me. And then I Googled that, and I eventually designed my own project that I wanted to do to challenge myself with multiplayer. And I planned that out before starting it. Like, I had a document, I don't know, it was 50 pages with a to-do list. Everything I needed to do. That's just how I work. And I color-coded it, like different priorities, etc., what should be done when, etc. And then I just created that project for, well, I did this first, and then the project. So the project was about 1 year. And I did the full motion of it. I published it to Steam, not to get it to be a full-on game. I wanted to go through everything. It looks bad, but it has a great multiplayer solution behind it. And yeah, I think we have time for some questions, and which I hope I'll be able to answer. We have one over there.
Hi there, my name is Eric, and I'd like to challenge your last statement there, don't fall for the multiplayer made easy, because I'm coming from a company with ambition to make multiplayer easy, because exactly what you talked about here is such a hassle to do all this bit packing and everything.
Yeah, can I just say this is for those who want to really work with as network engineers and work at your company, because you're doing this for others to have it easier.
Exactly.
I'm talking to network engineers, multiplayer programmers.
Exactly. Yeah, I'm absolutely right. But what is your opinion on this? Because this is, in itself, it's super hard. Definitely. It's so many ways to make mistakes here, but the added value to a game, a game just wants this to work, right? So what's your perspective of adding value to a multiplayer game? Where's the value for a game studio? Should they employ people like this, or should they come to an ordinal and buy the solution or get the solution for free? What's your opinion there?
For sure, if you're not dedicated to to do just multiplayer games, then I say go for solutions out there and see what works. But I also feel that if you're doing that, you kind of lock yourself in a place where you might be just reliant on those solutions, and then you want to make your studio more, you want to edit that game, you want to optimize the game, and that's hard to do with a third-party solution in there in between. And I've been at I've been at 3 different companies. 2 of them have gone through a solution, and then this holds us back now eventually. And then they still had the solution there, but they had gone around it and made custom code, and and the solution was there but not really used. And that's, I see it as the how do you say it in English? At the first steps into multiplayer. But I have a hard time myself, I'm talking for myself now, but I have a hard time seeing it as the complete solution for multiplayer in games, unfortunately. I can for sure be wrong. That's just my opinion.
No, but I agree. I mean, it's essential of the game itself. So source code needs to be provided for further optimization, for sure. But do you see that there is a way to make multiplayer even more innovative in this kind of technology aspects? Or is this kind of the foundation, and then the innovation comes in the gameplay later?
If you have a dedicated network engineer who likes working with this stuff, then I think you can do a lot more experimenting and new fun designs working source code. But for sort of general games, if you don't want to play around with it, then you can solve a lot to get your multiplayer game in a good state with a solution. But if you want to do something new and revolutionizing, I would say to go low level. For example, with Rocket League, for example, they took physics into multiplayer a bunch of years ago, and they had to be really innovative to solve that. And that, I think, would be hard to do without people that actually know multiplayer in this level, or this low level, so to speak.
Okay, thank you very much. Yeah.
Hi.
Hey.
I was just curious about something. In shooters, for example, sometimes people with bad internet, their player model will shift between 2 positions very quickly, kind of teleporting. And I was wondering, what is the cause of that? If you know what I'm talking about, maybe you don't. I don't know.
It's a hard question. I think it's specific to how they solve this local to remote issue.
Okay.
Some shooters don't really care much about it, because as in the Valve link there, for example, they take up that the server, when I shoot at your player is actually over there on your screen,
right,
but you're there on my screen.
Yeah.
So I shoot there and register that timestamp that your player was at in the interpolation. send that to the server, and the server can check, was this player there at this timestamp? And if true, then yes, I damaged you.
Okay.
If not, then I missed. So it can actually allow me to shoot you in past time. So the server stores states of your character over X number of frames, time steps. But that's a hard question, unfortunately, for me to answer. But it has to do with their replication and their solution to close in this gap, which they probably do if that happens.
Right. Yeah, thank you.
Hello. Thank you for your talk. It was very nice. I have two questions.
Yeah.
One which you said maybe you won't answer, which is about how tail tag actually works. So I'm just gonna try. Is the tail action, like grabbing someone's tail, is that predicted somehow?
No, it's not predicted. That's a good question, actually. I'm not gonna go into actual solutions, unfortunately. I didn't have time to set that up and get a proper presentation to go into solutions. But it's not predicted, no. Because if we were to predict it, then what happens if the prediction is wrong? Then you grab the tail, and then poof, it's gone, because the server says no. So it wouldn't work. Not for those specific things that need, that's the win condition, almost. Yeah. You can do it for collisions, because you can collide, it can go over there, and then the client receives a new snapshot for this, and the collision maybe didn't happen, so the snapshot is still over there instead of there. It would just soft reconciliate back to the position, and that works. But not those key parts. Those aren't. Those need a confirmation from the server, so it happens on the server. Then, what happens there? What does the client send to the server for the server to do that calculation? Because there's a discrepancy, as you saw also, what you see, what the server see, and what the other players see. So all the clients are seeing a different scene than what the server sees. No one sees exactly what's happening on the server. So it's it can be handled in many different ways, and it's handled server side.
Yeah.
Yeah.
Yeah, thank you. And the second question was, as someone on a project who is looking to hire network programmers, do you have any tips on how to find them? And then secondly, how to evaluate them?
Yeah, that's a good question. A lot of people, a lot of companies are looking for network programmers, and it's really hard to find. So I would say look for someone that is interested. They don't need to know everything. If they're interested, you can say that we have this problem. Please work on solving it. They will, if they're interested, they will read about it, they will pick it up, and they will eventually learn and solve it. We need more of those kinds of ways into multiplayer, because there's not many schools teaching multiplayer, and it's a complex workspace. It's a complex area. So I think companies need to hire people that want to work with it and have shown some, you don't need to show a project around it. You just need to maybe talk a little bit about remote replication, like understanding local server remote, for example. I can say one thing I've used when I interview is a simple visualization, so to speak. Or say you have a track going around, a race track or a running track, and they have two people on it, one traveling in one direction at a certain speed, and the other traveling the other direction at double the speed, where would they meet? And seeing someone stepping through that problem is quite like multiplayer problematization, or whatever it's called. It's because you have two different entities acting in a space, and they're supposed to interact somewhere or so. And I'm using such thought experiments on potential employees or co-workers. Yeah.
Yeah. Okay. Yeah. Thank you.
Thank you.
Hi.
Hi.
Great breakdown on the fundamentals. Really
Thank
good
you.
explanation. So maybe a hard open question, but do you have any counterintuitive examples of, or like epiphany things that you experienced, like this is not as I thought and I was blown away when I realized how it was made, or something like that?
How much is faked?
Oh,
It's
yeah.
so much prediction, and like if you purely do it like I shown here, there will be delays, like there will be issues, especially working with physics. And you have to fake it almost till you make it, so to speak, in multiplayer. So there's a lot that doesn't actually work as you would thought it works. But I guess I don't have any real examples. Not that pops to mind, nothing specific.
I might just add something that maybe you can agree. I feel sometimes it's like if you can convince the players they are playing the same game, nothing else matters.
Yeah, essentially that. Since no one really sees what happens on the server, they see a delayed version of everything.
Yeah.
And if it looks coherent, if it feels good, then it is good. And people have said throughout the conference, don't aim for perfection. It won't be perfect. It's good enough.
Yeah. Nice. Thanks.
Hello.
Hi there. So if you're looking for an entry-level job in the a multiplayer programmer, how low level would you recommend that one would need to go? That you go from the handshaking and do every single part and transport layer, or
I guess it depends on what you want to work with. If it's network programming, like the low-level network solution, handling packet management, messages, like building a packet, etc. Or if you want to work with multiplayer, like handling remote players and the motor tasks, etc.
more gameplay?
But I would say, as I said, you need the base of it, and I would the approach I did, I feel worked, and apparently did work for me, and I dug in quite deep. So I would recommend, but that's also, everyone is in different situation. I could work 40% at the hospital then, and do this over 1.5 years, around that. I didn't have to bother with living unemployed while doing it, for example. But yeah, the main thing is to be able to talk about it, to show that you understand flows in it. Because if you can show that, then you can also think around it and yeah, you've shown that you can stand on your own 2 feet a little bit. You won't need to do that joining as a junior, but you still need to be able to talk the same language. And I would recommend reading everything. I don't have a better
I'm
answer.
satisfied with the answer. Thanks.
Thanks.
So thanks for the great talk. I teach game design at the university, and I see some of my game design students in the audience, which I think is great because designers need to know about this stuff. So do you have any advice for designers on how to design mechanics that work well in multiplayer and perhaps make your life a bit easier?
Bring the speed down. Everything that goes fast is hard in multiplayer. And if you can have something toggle something, for example, then it can be toggled by the server and sent back, so it doesn't need to be actually predicted. So like the tail tag question, it's the server doing the action and then sending that back to the clients, and then it happens. And with the speed thing, the more speed you have, the more distance these 105 milliseconds from the local to remote, the more distance it will be, and the more hard it will be to actually network. So if you want to make it easier to make a multiplayer game, bring down the speed of it and make it so it doesn't need to react instantly. It's okay to have, when you're opening a door, or if that should be significant, make it a timer so you actually pull the handle while you get the message back that yes, you're okay to open this door because something should trigger for someone else or something. Just think about the server aspect of it, that the server should be authoritative over important actions. And that needs to be spread to everyone then.
So every game should be turn-based, is what I'm hearing, right?
Maybe the first multiplayer game could be turn-based.
Thank you.
Mine wasn't, though. I did a hard... that was also a part that I said in the beginning. I challenged myself with my first game because I read up and then I picked out the parts that I found difficult, which is physics, like working with rigid bodies in multiplayer. So I did a round planet with a custom gravity and projectiles that follow the gravity and projectiles that move in the real world so you can dodge them instead of like shooter games that have ray costs instantly. And this is really hard. And I also wanted it to be able to be played solo, co-op, and competitive PvP. So I had to do AIs, and I had to accommodate 64 players in it. And that required me to work with variable optimization or bit optimizations. So I put in these things in my project that forced me to solve solutions or solve problems with my own solutions. Yeah. Thank you very much for listening.